Okay, so yeah, so let's have a look at this. So our function is 1/4 x squared, okay? We do this a lot in math. We want to use approximations that are easy to approximate more difficult curves. Okay, this isn't that difficult to curve, but pretend it is. We've got this red curve that's a curvy curve, and then we want to make some approximations. So in the vicinity of x equals 2, we want to make some predictions about the behavior of the function. Okay, is the blue function a good model? Like, what if I want to say I want to be from x equals 2, I want to go plus or minus 5. Is a blue model a good model in that case? It's terrible, isn't it? It's terrible. If I go backwards by 5 at -3, that's where the red function is, and that's where the blue function predicts it should be. It's terrible, right?
Perfect.
But under certain conditions, it might be okay, right? What would I have to do maybe to make the blue model a good model?
It has to be linear.
Okay, yeah, in other words, where might I look?
These ones.
What would I have to do to this graph in order for the blue model to be an acceptable model? No, I already did that. The blue model is tangent to the red curve at 2. Everybody agree? In fact, let me go ahead and put that point 2 in there. So there's an important point. No, you're making it too hard. I don't have to do any of that fancy stuff. All I'm saying is, if I zoom in, look what happens.
But your original stipulation was that it plus or minus 5.
Right, so that was no good. So now my next question is, okay, so plus or minus 5 is no good, right? But is there some interval in which it would be pretty good? Yeah, well, I'm starting to find one, aren't I? I mean, if you look at this, now there's 2. I mean, if I go plus or minus 0.05, boy, that's pretty good, right? That blue function is a pretty good predictor of the behavior of the red function, right? So that's called a linearization or a linear approximation, right? And it's really simple. All it is, literally, all it is just the equation of the line tangent to the curve. The question is just, is it an acceptable model? And so we're going to talk about some ways that we can determine if it is or isn't, right? Does that make sense?
Would it be similar to the thing that we did, I believe, in physics with the finding the R and whatnot?
It's kind of similar. Yeah, it is. In fact, it's actually maybe a better measure than what we did there. That was a little bit hokey. I mean, that's what that's for. But attaching a percentage to the strength of correlation is a little hokey. I mean, it's just a good way to think about it, but it's not truly what it means. Okay, this is different though. So let's draw a picture. Okay, and I'll put this in my online notes, so you don't even really have to draw this picture. Just really follow along. Okay, so let's take a function, and this is, I probably shouldn't use a real pen on my whiteboard here. What if I use a virtual pen? Remember, calculus is all about pictures. This is an important picture. Kind of. Okay. That's gonna be about perfect. Oh man, I'm so excited about that one. Look at that. It's not quite symmetrical, but look at, oh no.
You need to put it way down. Yeah.
Is that getting better? Am I changing anything?
No, that's picking it back up.
Yeah, you're just picking it back up. You're sizing
No, it
the
looks the
object,
exact
not
same.
moving it.
Oh, but this does something, right? Serious?
Yeah, you're not moving it, you're just changing the size of it.
Oh, that does something right there. That does. See, that's helping me. There we go. Okay.
Okay, I don't know
That's
what
pretty
happened,
good.
but it
We get
works.
the idea. Right. We get the idea. Okay, so this is my linearization, right? So we're going to call this is my function f of x. Okay? Let's say that this is the point x equals c. Okay? And we're going to call this distance right here delta x. I should put that on the bottom. It's going to get crowded. Oh, it's kind of. So then this point right here is just going to be, that x value is just going to be c plus delta x. Okay? And so, this sounds familiar, isn't it? Right, so we got these 2 points. This looks an awful lot like the picture that we drew to define the derivative, right, with the difference quotient. Okay, it's similar. So the coordinates then of this point and this point are what? This one's going to be c f of c, and this one is okay, good. All right. So then, what about? I want to go back here. I'm going to copy. Boy, I can be so tricky with this. Oh, I'm getting to play with all my toys today. This is good stuff. There. Oh, yeah. Oh, that's good stuff. Okay, so then I could call this distance right here, from here down to there. I'm going to call that delta y, right? Okay, so this distance from there down to there is delta y. Okay. You mean this one right here?
No, the part below the line. Yeah. Between the lines. So there's delta y and then this part from,
Right there?
yeah.
That's delta x.
Well, yeah, no, but then up from there is just y.
Oh, that's just y, right? That's just f of c, right?
Come on,
Okay.
read between the lines.
But the change in y, what I'm really saying is that's the change in the function, right? So we could define this up here. Delta y is really just f of c plus delta x minus f of c, right?
Yeah.
Okay, but this function is approximated in the neighborhood of c. It's approximated by the linearization, right? It's approximated by the green line. So let's explore that a little bit. So what is going to be the value of this value right here? In fact, what are going to be, maybe we can go one step further and let's say, well, yeah, let's just do that. What's that going to be? Because this does relate to some stuff that we talked about earlier.
G of c plus delta x.
Okay. Now, hold on here. So, the green line is tangent to the blue line, right?
Yeah.
So what can we say about the slope of the green line?
Oh, yeah.
It's the derivative of f of x evaluated at c, isn't it? Right? Definition of a derivative. Aha. Okay, so the slope of the green line, which we'll call the tangent line in this case, is just equal to f prime of c. Aha. And if this distance right here is delta x, we could just make a right triangle out of this, couldn't we? Right? We know slope equals rise over run. And so that's really equal to what we might call, we're just going to call this dy. Okay? So that distance right there is dy.
Is that distance of y? or
Well,
is that
it's
derivative
Yeah, it really, it looks like a piece of the derivative, doesn't it? Right, because f prime of c, the derivative is really just f prime of, is just dy dx, isn't it? Right? And so what would my dx be? Well, okay, we called it delta x, but let's also call it dx for the purposes of our derivative, right?
You're recording this, right?
Yes.
I am recording this, yes. Okay, and so then our derivative, dy dx, that's really just equal to f prime of c, isn't it? Right? Agreed? There it is. So if I were to solve that for dy, what is dy equal to in that equation? F prime of c times dx. Okay, now that actually means something in the context of our picture, doesn't it? Right, if we're calling this distance right here dx, and that distance right there dy, then yeah, that does mean something. Okay, and so what we'll really end up here with then is this, what we're going to call the differential approximation, which is going to be the approximate change in the function over delta x or dx, whatever you want to call it, is really just equal to f prime of c times dx, or delta x, whatever you choose to call it, right? So the slope of the tangent line times delta x is going to give you how much the line has changed, which is going to be the approximation of what quantity? Not dy. Delta y, right? You see that?
Oh, we're trying to compare the two.
Right. So we come up with what's called a differential approximation. Okay, so we end up with dy is always equal to f prime of x times dx. In fact, all that implies is just a difference in notation, right? So if I've got something like, for example, f of x equals 3x squared, what's f prime of x? 6x, right? So then by definition, dy dx equals 6x. Okay? We could write this in what's called differential form, the same derivative, and then it just looks like dy equals 6x dx. Okay? That might seem kind of confusing in a way. Why would we do that? Well, you're going to see I'm going to give you the biggest reason we do that. Because when we move into the next chapter and we talk about anti-differentiation, which just reverses the process, in order to do that, in order to solve those kinds of equations, antiderivatives, which we'll come to call integrals, we have to write the function as a differential equation, that just means an equation with a derivative in it. We'll get there next chapter, in differential form. Okay, we don't want to write it as dy dx equals something anymore. Now we have to break this up into differential form. And I'll give you just a quick example. And I know this is jumping ahead, but to me personally, this always helped me in college when people would say, okay, here's what you're going to do with this. You're not going to understand this, but at least you'll see where the context is coming from, right? So for example, if we wanted to find, let's say we have the differential equation, f prime of x equals x squared. I'm just going to go to the next page. Equals x squared. Okay, so we could write that as, for example, dy dx equals x squared, right? Let's just change the format a little bit. We're just changing, and remember we talked about how a derivative can be written in a bunch of different ways, but they all mean the same thing. This would be the ratio form, that's the function form, right? So dy dx equals x squared. To solve that for y, to solve that differential equation, and really what that's going to mean next chapter, and we'll come back and have some much more in-depth conversations about this, we're just trying to find the function whose derivative is that, right? You get the idea? What would we differentiate to get that answer, right? Okay, that's generally a harder proposition than just taking a derivative. Yes?
So when you're getting the dy equals x squared times dx, are you just cross multiplying
Okay, no, yeah, we are, exactly. All we're doing is just putting this in differential form, and the great thing about this, and this is what I just love about math, it's so self-consistent. So it works that if we just do algebra with this notation, it means something, right? It really does. It just means we're putting this in a different, and next chapter, you'll actually kind of get some insight into what that means. What does it mean to say a dx? What does that really mean? What is, it actually kind of just means a little piece of x. It means an infinitesimally small nudge in the x direction. And we'll even go further this year where we'll do crazy things like this, where we'll say things like v prime of x equals, I don't know, 3x squared. And now we'll say, okay, that's dv dx, right? So dv dx, well, if that's dv dx, then dv equals 3x squared dx. So we're evidently talking about some volume where we've got this thing broken down into a height of x squared in little tiny pieces that are dxy. And we're just going to add a bunch of those up, and we'll actually end up being able to do what's called a definite integral and add up some real volumes of real mathematical things, right? Okay, but I'm getting ahead of myself. Let's just look at this one for a second. If dy dx equals x squared, here's where we're ultimately going to go with this. And this is, I really want to get there because it's really cool stuff. We'll just rewrite this as dy equals x squared dx. And then we're going to do, looks really mysterious now, but it looks, I mean, you guys will know this stuff soon. We will integrate both sides, and that means we're going to find the derivative of what equals that and the derivative of what equals that. This is an antiderivative. Well, what would I differentiate to get dy? Y, exactly. You already have a sense of this, right? What would I differentiate to get x cubed?
1/3.
Oh, sorry, x squared. I screwed it up.
What, 1x?
1/3 x cubed, right? So I'd get x cubed over 3. And it turns out that really this could have been a y plus some constant, and we never would have known it because when we differentiated, the constant would have disappeared, right? Everybody agree? And then over here, we would have had plus some other constant. And so when we put all this stuff together, we could really just skip down to this step. We would end up with y equals x cubed over 3 plus some combined constant called c, right? And that's the constant of integration. But you kind of get an idea. Now that's way, way ahead. That's many steps ahead of where we are now. But you see that there is going to be some practical benefit to writing it in this new notation called differential notation. That's all it is, right? But there's even a more, with the stuff we're talking about now, there's even a more direct benefit of that because it actually means something in terms of our picture, right? Of these linearizations. Because we're saying that literally dy is equal to that, right? And so if I want to get an approximation, if my function is, for example, when are we out of here?
1 minute 3.
Oh, shoot. I hate Mondays. So if our function was, let's just say it happens to be x squared, well then all we got to do is say, and let's say c is 2, how about, okay? Then all I'd have to do is say, well, if we're going to travel some distance 0.1 out there, right? Then all I'd have to do is say, okay, our answer is going to be f prime of c, which is 2, times 0.1. How cool is that? F prime of 2 would just be what, 4?
Yeah.
Right? Times 0.01 would be 0.4. So that approximates the amount the function, isn't that cool? Approximates the amount the function changes. Okay, we'll get back to that.